Alright, so first a bit of a refresher. If you recall, final position minus initial position is equal to the change in position. We can write this as delta x. Remember that delta means change in. And anytime we use the word change in mathematically, that can be written out as a final value minus an initial value. Now, as we mentioned earlier, delta x can also be called displacement. So change in position and displacement, those two terms are synonymous with each other and can be used interchangeably. If we were to take the change in position, or displacement, and divide it by the change in time, we would determine the average velocity of a given body. Remember that velocity can be positive or negative. A positive velocity means that something is traveling in the positive direction, and a negative velocity implies that something is traveling in a negative direction. Don't forget as well that when we talk about change in time, we're often not going to say the words change in time because usually the initial time is 0. So generally speaking, we'll see just time on its own. But whenever we're dividing by the time in this case, we're really talking about the change in time, the time interval during which, for instance, the displacement occurred. And again, this is how we would calculate our average velocity. Don't forget, subscripts are used to describe variables further. So you'll often see us write out the displacement divided by the time will give you the average velocity during that time. Let's try a few displacement and velocity examples. We'll use this Triceratops to help us out. Let's imagine that the Triceratops begins at a location that we can call the origin, or a 0-meter position. We'll imagine that all of the numbers on this number line are in fact in meters, which is a very typical SI unit for measuring out position and thus also displacement. Now let's imagine that the Triceratops moves from the origin to, say, the 8-meter position. In this case, we could say that the Triceratops has a displacement of 8 meters, as his final position is 8 meters and his initial position was 0 meters, thus giving us a displacement of 8 meters. If he were to perform this displacement in 2 seconds, that would mean that his displacement of 8 meters took place in 2 seconds, which means that his actual average velocity during those 2 seconds would be 4 meters per second. Meters per second is a very typical unit for a velocity. Notice that the Triceratops had a positive velocity and was heading in the positive direction during his trip. Now if the Triceratops were to move from the 8-meter position to the negative 8-meter position, we could calculate that he had a displacement of negative 16 meters. His final position was negative 8 meters. His initial position, which we will subtract, was positive 8 meters, which means his displacement, or change in x, is negative 16 meters. If that trip took 4 seconds, then his displacement of negative 16 meters, which took place in 4 seconds, would indicate that he had an average velocity of 4, or I should say negative 4 meters per second. Notice that the Triceratops was headed in the negative direction on that last trip, and thus his velocity was also negative. Again, the negative or positive aspect of velocity implies the direction of the motion. So one last calculation. If the Triceratops were to move from the negative 8-meter position to the negative 4-meter position, notice that the Triceratops actually has a displacement of positive 4. This, of course, would be because we have the final position as negative 4 meters minus the initial position of negative 8 meters, which would give us an answer of positive 4 meters. Notice that he is displacing himself such that his position is becoming more and more positive. If this took place in 1 second, his velocity would also be positive 4 meters per second. In other words, 4 meters divided by 1 second gives you 4 meters per second. Note that although the Triceratops is on the negative side of the number line, he still has a positive displacement as well as a positive velocity. This again is because the velocity, whether it is positive or negative, is not a matter of where on the number line you are, but rather the direction that you are traveling. You can see that the Triceratops has traveled further and further to the right. His displacement is becoming more and more positive. He is heading in the positive direction. Positive direction again on the number line, typical number line being to the right. And hopefully you still recall that this is called a sign convention. As one can imagine, velocities do not always stay the same. In fact, they frequently don't. Every day we go from moving to not moving and back to moving. Whenever we do this, we are changing our velocity. By its very nature, change has to take place in a certain amount of time. Whenever we change our velocity in a certain amount of time, what we are actually doing is we are accelerating. The way we can determine our acceleration is with a formula that is very similar to change in position over change in time. We can look at our change in velocity, our final velocity, minus our initial velocity, over our change in time, which again can really simply be stated as time, as generally speaking the initial time is 0, so final time minus initial time, which in this case is 0, will give you time. So acceleration can be stated as the rate of change in velocity. Again, remember, rate means a value over time, so a rate of change in velocity. So whenever you are accelerating, you can expect to see a change in velocity. Remember, there are more than one way to change velocity. We can make it larger, that's speeding up. We can make it smaller, that's slowing down. But we can also change its direction, going from positive to negative. All three of these things are ways in which a body can accelerate. If a body is speeding up, slowing down, or changing direction, it is accelerating. So, to reiterate, acceleration is the rate of change in velocity. Again, delta V representing the rate, over T representing the rate, delta representing change in. In other words, we can say that acceleration explains how quickly or slowly, or just how, our velocity is changing. Consequently, the units for acceleration that are most often seen in physics are meters per second per second. This can also be written as meters per second squared. Like displacement and velocity, acceleration is a vector quantity. This means it also has a direction and a magnitude. When I see you in class next time, the question that I would like to discuss is, what does it mean to have a negative acceleration? We already know that a negative displacement means that you are moving towards a position that is more negative than your previous position. We know that a negative velocity implies that you are moving in the negative direction or traveling in the negative direction. But what does a negative acceleration mean? That is the question that I will conclude with, and on Monday, that will be, or the next time I see you, that will be the first thing that we talk about. Alright, see you next time in class.